Newton's second law of motion allowed us to introduce the concept of mass or inertial mass, which is a fundamental property of bodies in nature. There are many different methods to measure the mass of bodies, and we will first discuss the dynamic measurement of mass. Let us consider two bodies with masses m1 and m2. For example, an iron cylinder with the mass of m1, and a lead cylinder with the mass of m2, where we will approximate the cylinders with point masses in motion. The second law of motion tells us if a force F is applied to both the point masses, then the same force produces the accelerations a1 and a2 on the bodies. Since the force acting on the point masses is the same, the accelerations a1 and a2 point in the same direction and only their magnitudes are different. Therefore, the magnitude of the force F is equal to the mass m1 times the magnitude of the acceleration a1, which is also equal to the product of the mass m2 and the magnitude of the acceleration a2. It follows from this equation that the ratio of the masses is inversely proportional to the ratio of the accelerations, that is, the ratio of m2 to m1 is equal to the ratio of a1 to a2. As a result, we can determine the relationship between the masses of two bodies by measuring the ratio of their accelerations produced by a given force. That can be done in the experiment with the suspended cylinders, which are attached to two springs, provided the mass of the springs is negligible to those of the bodies. In this experiment setup, the acceleration of the cylinders at the maximum amplitude is inversely proportional to the square of the period of their harmonic oscillation. Then we only need to measure the period t of the harmonic oscillations of the two bodies with the same maximum amplitude x0, for example with 1 cm. We have already seen that the springs exert the same force F0 on the cylinders at the maximum amplitude x0 of their oscillation. We have also found that the square of the period t for the lead cylinder is 1.5 greater than the one measured for the iron cylinder. That is, the acceleration of the lead cylinder at the maximum amplitude is equal to the acceleration a0 of the iron cylinder divided by 1.5. The ratio of the mass m2 to the mass m1 is equal to the acceleration a1 to the acceleration a2, and the right-hand side can be written as the ratio of t2 squared to t1 squared. Here t1 and t2 are the periods of the oscillations performed by the cylinders with the mass m1 and m2, respectively. Since t2 squared is equal to 1.5 times t1 squared, the ratio of the masses is equal to 1.5. That is, a lead cylinder is 1.5 times more massive than the iron cylinder. Therefore, this experiment provides a relatively precise method to measure mass ratios. By measuring the ratio of the periods for the oscillations of bodies with different masses, we could determine the ratio of their masses. Here we have determined the ratio of masses of different bodies by measuring the periods of their oscillations produced by the same elastic force of the springs. We can repeat this measurement with other maximum amplitudes of oscillation of the cylinders, for example with 2 or 3 centimeters. Then the elastic force acting on the bodies at the maximum amplitude is 2 and 3 times F0, that is 2 or 3 times greater than the force accelerating the bodies at the maximum amplitude of 1 centimeter. We find that the periods of the oscillations remain the same, that is, the square of the period for the oscillating lead cylinder is 1.5 times greater than the square of the one measured for the iron cylinder. The acceleration at the maximum amplitude of 1 centimeter is 1.5 times less than the one measured for the iron cylinder. For the maximum amplitudes of 2 and 3 centimeters, the accelerations are 2 times a0 divided by 1.5, and 3 times a0 divided by 1.5 respectively. These results can be substituted in the second law for the cylinders performing simple harmonic motion, which gives the following expressions. 2 times F0 is equal to the mass m1 times 2 times a0, which is equal to the mass m2 times the ratio of 2 times a0 to 1.5. And 3 times F0 is equal to the mass m1 times 3 times a0, which is equal to the mass m2 times the ratio of 3 times a0 to 1.5. Then we have demonstrated that the ratio of the masses remains the same, if we apply different amount forces by modifying the maximum amplitudes or even using springs with different elastic properties. This result proves that the ratio of the masses is only the property of the two bodies, and not related with the experiment setup. Now we can attach the iron cylinder to the lead cylinder, and measure the period of the simple harmonic motion performed by the compound of the cylinders. For the maximum amplitude of 1 centimeter, the force applied on the double cylinder is still equal to F0. By performing the measurement, we find that the square of the period of the oscillation is 2.5 times greater than the square of the one measured in the case of the single iron cylinder. That is, the ratio between the accelerations of the double cylinder and the single one is equal to 2.5. We have already seen that the ratio of the mass of the lead cylinder to the mass of the iron one is equal to 1.5, that is, the lead cylinder is 1.5 more massive than the iron cylinder. This experiment shows that the mass ratio of the double cylinder to the single iron cylinder is 2.5, at least with a relative error of a few percent. That is, the compound of cylinders is 2.5 times more massive than the iron cylinder. Then we conclude that the mass of the compound of cylinders is the sum of the masses of the individual cylinders. In generally, we can also demonstrate that the mass of the compound bodies is equal to the sum of the masses of their components, that is, the mass is an additive or a scalar quantity. We have seen that the dynamic measurement of the mass is applied to measure the ratios between the masses of different bodies, which allows us to define the unit of mass in physics. With the dynamic method, we can measure mass ratios for any series of arbitrary bodies with masses m1, m2, m3 and so forth. If we choose the mass m1 as a unit to measure mass, then the masses m2, m3 and so forth can be determined in unit of m1. In this example we chose the cube with the mass m1 as the unit in the mass measurement, and it has a unit mass now. Then we measure the ratio of the mass m2 of the cylinder to the unit mass m1, which is equal to 4. That is, the mass of the cylinder is equal to 4 measured in unit of m1. Similarly, we can measure the ratio of the mass m3 of the sphere to the unit mass m1, which is equal to 3. Then the mass of the sphere is equal to 3 measured in unit of m1. This procedure can be repeated for any member in the series of the bodies. Based on this principle, we can introduce the unit of mass in physics. The SI unit of mass is the kilogram, which is 1000 grams. The abbreviation of gram is g, and the unit symbol of kilogram is kg. The original definition of the kilogram is the mass of 1 liter or about 1 cubic decimeter of distilled water, at a temperature of 4 degrees Celsius. The modern definition of the SI unit of mass is the standard kilogram, which was in use until 2011. The standard kilogram is defined as the mass of a solid cylinder with a height equal to its diameter. The cylinder was made of 90% platinum and 10% iridium alloy, and one of its replica can be seen in the photo. Since the solid cylinder used to define the kilogram had lost a mass of about 50 microgram during 100 years, the kilogram was redefined by using the Planck constant, which has the unit of kilogram times meter squared per second squared. In order to determine the mass equivalent to 1 kilogram, the so-called Kibble balance was applied, which is a device measuring mass with a high precision. The Kibble balance in the photo is based on equalizing the force produced by a test mass with another force produced when an electrical current is run through a coil of wire immersed in a surrounding magnetic field. Here the electric current is measured using two constants, both defined in the terms of Planck's constant and the charge of the electron. The kilogram determined with this apparatus is also called as electric kilogram. After having introduced the unit of mass in physics, we give a brief overview on the basic properties of mass. As already mentioned, the mass is one of the most important fundamental properties of the bodies or the matter. If we take a simple body in our everyday environment, for example a ball, and measure its mass at a given instance of time, let us say at t1, and we measure it at another instance of time, let us say t2, then we will find that the masses measured at different instances of time are the same. That is, the mass of a body does not depend on time. If we perform the mass measurement of the ball in a given position, which is described by the position vector r1 with respect to a reference point, and we repeat the measurement in another position described by the position vector r2, then we will find that the masses measured in different positions in space are the same. That is, the mass of a body does not depend on space. If we measure the mass of the ball moving with the velocity v1, and we repeat the mass measurement when the ball travels with the velocity v2, then we will find that the masses measured in the two different states of motion are the same. That is, the mass of a body does not depend on its velocity or its state of motion. Lastly, if we measure the mass of the ball which the force F1 acts on, and we repeat the mass measurement when the force F2 acts on the ball, then we find that masses measured under the actions of different forces are the same. That is, the mass of a body does not depend on any force acting on the body. We can summarize these findings as follows. The mass of a body is constant, independent of time, space, the motion of the body, and the forces acting on the body in macroscopic scale and not for very large velocity. These properties of mass seem to be evident. However, the restriction that these statements are valid only on macroscopic scale and not for very large velocity indicates the opposite. In classical mechanics we still accept the validity of these statements, and use them as a satisfying description of the properties of mass. We can also state that the masses of two bodies are equal, if the same force produces the same acceleration for the two bodies. That is, the second law of motion tells us that the force F acting on a body is equal to the mass m of the body, times its acceleration a. By virtue of the second law, if the force F acts on the bodies with the mass m1 and m2, then produces the accelerations a1 and a2. If the accelerations a and a2 are the same, then the mass m1 is equal to the mass m2, that is, the bodies have the same mass. We can also demonstrate that bodies made of different materials, with different sizes, shapes, temperatures or colors, or bodies in different states of matter can have the same masses. At the same time, bodies made of the same material can still have different masses. The last property of mass we discuss here is extremely important, not only in mechanics but also in all the branches of physics. This property is the conservation of mass. The law of conservation of mass was proven experimentally by Lomonosov in 1756 and by Lavoisier in 1773, and it states the following. The total mass of the bodies in a system remains the same even if chemical reactions or phase transitions take place in the system. This principle claims that the conservation of mass holds in any situation. The first situation or case is the mechanical transformation of a system, where the mass of a body or collection of bodies never changes, no matter how the constituent parts rearrange themselves. Here we can see a system indicated with a box within three different bodies of the masses m1, m2 and m3. In the left-hand side, the system is shown in a given configuration, where the bodies in motion are at given positions. In the right-hand side, the bodies already occupy different positions, and they might also have a different state of motion after their rearrangement. The conservation law states that even if the system has a completely different mechanical state, the total mass of the system, that is the sum of the masses m1, m2 and m3 of the bodies is constant, and it remains the same. The second case is related with chemical reactions, which were studied by Lomonosov and Lavoisier in their experiments. They proved that mass is neither created nor destroyed by chemical reactions or physical transformations. In other words, in a chemical reaction, the mass of the products will always be equal to the mass of the reactants. In any of the four basic types of chemical reactions seen in the figure, such as a synthesis or combination, a chemical decomposition, a single replacement, and a double replacement, the total sum of the mass of individual reactants is equal to the total sum of the mass of the products. The third case where the conservation of mass hold is phase transitions, where the total mass of the matter transforming from one state to another one is constant. Solid materials can melt into a liquid or liquids can freeze and solidify. Liquids can evaporate and become gas, or gases can condense to a liquid. In deposition, gas transforms into a solid, and in sublimation solids convert to gases. Whichever phase transition happens in a system, and whichever phases exist together, the total sum of the masses of the gas phase, the fluid phase and the solid phase is constant. Therefore, we conclude that matter can change forms but its mass is always conserved. As a result, different measurements of the mass of a body taken under various circumstances is always the same, that is, the mass of a body or of a collection of bodies in a system is independent of the state of motion. However, this statement holds only for moving bodies with velocities that are small compared to the speed of light. After having introduced the SI unit of mass, we can also determine the SI unit of force. In kinematics, length and time are fundamental quantities, and their SI units are meter and second, respectively. The unit of any derived quantity, such as velocity and acceleration, is also derived from the units of the fundamental quantities. We saw that the unit of velocity is given by length divided by time, that is, its SI unit is meter per second, and the unit of acceleration is equal to length divided by time squared, which is meter per second squared in SI units. In dynamics, mass is introduced as another fundamental quantity and its SI unit is kilogram. In mechanics, these three fundamental quantities, that is length, time and mass, are sufficient to derive all the other physical quantities. As an initiative by Gauss and Weber, the system of physical units was introduced 1836, where length, time and mass together with their units were considered to be the fundamental quantities in units. We have already denoted length, time and mass with L, T and M, respectively, and their units were written as these letters in square brackets. Then the units of all derived physical quantities can be derived from the fundamental units, based on the laws and definitions in physics. The unit of any derived quantity Q has the form L raised to the power alpha, times M raised to the power beta, times T raised to the power gamma, where alpha, beta and gamma are integer numbers in mechanics. If we specify the fundamental units in SI, then we can write it as meter raised to the power alpha, times kilogram raised to the power beta, times second raised to the power gamma. Based on this system of units, we can derive the unit of force now. Force is introduced in Newton's second law of motion, which tells us that the force F acting on a body is equal to the mass m of the body times its acceleration a. Then the unit of force is equal to the unit of mass times the unit of acceleration. This expression can be written as the unit of mass, times the unit of length, times the unit of time raised to the power of -2. Now we can give the unit of force in SI, which is kilogram times meter per second squared. The SI unit of force is also known as Newton, that is 1 Newton is equal to 1 kilogram times meter per second squared. In other words, 1 Newton is the force required to accelerate 1 kilogram of mass at the rate of 1 meter per second squared in the direction of the applied force. For example, we can easily determine the magnitude of the gravitational force acting on any object. If a mass of 1 kilogram rests on a table, the downward force on the table is equal to 9.81 newtons. We have already studied free fall and projectile motion in kinematics, and we continue the study of these phenomena in dynamics by introducing the concept of weight. In kinematics we have the following findings. A body that falls or a projectile that travels through a vacuum has a gravitational acceleration, denoted by g. The average value of this acceleration is 9.81 meter per second squared at sea level and is directed downward. Since free-falling bodies or projectiles has acceleration, we conclude from Newton's second law that a force is exerted on a body in free fall or on a projectile by the Earth, which is called gravitational force. If the mass of the free-falling body or the projectile is m, then the magnitude of the gravitational force is equal to the mass m times the gravitational acceleration g, and is directed downward. This gravitational force acting on the body is called the weight of the body, and denoted by the capital letter G. That is, the weight g of a body is the force exerted on it by the gravity of Earth, and it is given by the mass m times the gravitational acceleration g. Experience taught us that the gravitational acceleration is the same for every object at a given location on the Earth's surface, but it depends on the location. That is, the constant, downward pointing vectors of the gravitational acceleration at every point near the Earth's surface are only used as an approximation. Therefore, the weight of a body measured at a given location is proportional to its mass but changes with the location, as opposed to its mass, which is an inherent property of the bodies and does not depend on space. For example, the weight of a body with the mass of 1 kilogram at sea level is equal to 9.81 kilogram meter per second squared at the latitude of 45 degrees, whereas it is equal to 9.78 kilogram meter per second at the equator, and 9.83 kilogram meter per second at the poles of the Earth. Unlike mass, the weight is not exclusively a property of the bodies. But rather, it is a force depending on the location on the Earth. The concept of weight allows us to measure force. The measurement of force based on balancing the weight of the bodies is called static measurement. One of the possible methods for static measurement of force is the following. If a body of a mass m is suspended from a spring, then the spring stretches a certain distance and the body stays at rest. The second law of motion tells us if the body is at rest, that is, its acceleration is 0, then the force acting on the body must vanish. However, there are two forces acting on the body now. The first one is the gravitational force pulling the body downward, even if the body is at rest. This force is represented by the weight g of the body, which is equal to the mass m of the body times the gravitational acceleration g. The second force acting on the body is the elastic force due to the stretch of the spring, and the amplitude of the force Fs exerted by the spring is equal to the weight g, but this force acts in the opposite direction. That is, Fs is equal to minus g. The downward pull on the body due to the gravitational force is compensated by the elastic force pulling the body upward. The net force acting on the body is the vector sum of these forces, which vanishes since the two forces have the same magnitude but the opposite direction. Therefore the net force F is equal to the weight g of the body plus the force Fs exerted on the body by the spring, which gives 0. Since the net force vanishes, the forces acting on the body are in balance, and the body remains at rest. We can study this balance by applying a series of bodies with the masses m1, m2 and so forth, which have the weights m1 times g, m2 times g and so forth. If the suspend these bodies from the string, then we see that the greater the weight of the body is, the greater the distance the string stretches. Here the distances of the stretch are denoted with d1, d2 and so forth. If the distance the spring stretches remains small, then the distance is proportional to the force stretching the spring, that is d1 is proportional to m1 times g, d2 is proportional to m2 times g, and so forth. The proportionality between the distance the spring stretches and the weight of the load suspended from the string can be used to measure the amount of force exerted on the spring by a load at rest, which is the operating principle of spring dynamometers. Since the measurement happens in the balance of forces, that is when the load suspended from the spring is at rest, we call this method the static measurement of force. Spring dynamometers are also called spring balance. Here we can see such a device, which consists of a metal spring on a two-part mounting. One end of the spring is fixed, and the other one has a hook or an eye for the suspension of the load exerting the force we are trying to measure. We can read the amount of force off a scale calibrated in units of force, that is in the units of mass times acceleration. We also show another dynamometer with a scale on a dial. Dial dynamometers normally use a sturdy metal spring, and their measuring range can be several order of magnitude greater than the one of the simple spring balance. Force can also be measured by comparing its magnitude with a known weight, for example by applying a single fixed pulley with a rope passing over it. If a body with the mass m is suspended from one end of the rope, we can hold the other end in our hand. The muscular force F can be applied to keep the suspended body at rest. Then the applied force must be equal to the weight of the body, which is given by the mass m times the gravitational acceleration g. The direction of the applied force does not need to be opposite to the one of the gravitational force. It can have an arbitrary direction, since the pulley can convert the direction of the gravitational force without changing its magnitude. Now we summarize the basic elements of the principle used by the static measurement of force, which helps us to compare the static and the dynamic methods. In the static measurement of force, a force of unknown magnitude is compensated with another force, which has a known amplitude, for example the elastic force of a given spring or a weight of a given body. In the examples we had a ball with the weight g, which is equal to the mass m of the ball times the gravitational acceleration g. If the mass of the ball is unknown or the precise value of the gravitational acceleration is not determined at the location of the measurement, then the magnitude of the force exerted by the ball, that is its weight, is unknown. If we suspend the ball from a spring or a rope passing over a pulley, where the another body with a given mass is attached to the other end of the rope, then the elastic force of a spring or the weight of a body has a known magnitude. This known force can be used to compensate the unknown force g. The system in which examine the force balance consists of the apparatus providing the compensation force together with the ball exerting the unknown force. The principle of the method is that the elastic force of the spring or the weight of the body used to compensate the force is known. If the unknown force exerted by the ball is compensated, then the forces in the system are balanced and the system is at rest. Now we can compare the static measurement of force with the dynamic method. In the static measurement of force, we can apply a relatively simple apparatus, which allows us to use some convenient method for the measurement. In the dynamic measurement of force, we need a more complicated apparatus, which makes the measurement method less convenient. The method applied in the static measurement of force is based on the effect of some static force producing deformation of bodies, which the force acts on. In the dynamic measurement of force, the method is based on the effect of some dynamic force accelerating bodies which the force acts on. We saw that springs are stretched by a weight attached to them. In fact, forces acting on any macroscopic object cause deformations, which are discernible in the case of springs and other elastic bodies, but less discernible in the case of non-elastic ones. For example, books placed on a table have a weight g, and exert this force on the surface of the table. As a result, the surface deformation of the table causes a deformation force Fd compensating the weight g of the books. Since these forces are balanced, the books remain at rest. The fact that the weight of a body is proportional to its mass allows us to perform a simple but accurate measurement of mass. We place two bodies with the mass m1 and m2 on two pans suspended from a fixed pulley. This system only remains at rest if the bodies have the same weight and the forces in the system are balanced. We suppose that the gravitational acceleration g is also the same everywhere in the system with a relatively small size, and we can write for the weight balance of the bodies that the mass m1 times the gravitational acceleration g is equal to the mass m2 times g. Since g is the same at the locations of the two bodies, it is constant in this equation. Therefore, the mass m1 is equal to the mass m2. If the mass m1 is unknown and the mass m2 is known, then the body of the mass m2 can be used to determine the mass m1. Since the static measurement of mass is based on the force balance, or the balance of weight, the instruments used for such measurements are known as balance or balance scale. Here we can see two balance scales, a traditional one in the left-hand side, and a Roberval balance in the right-hand side. If we have a set of bodies with different mass, we can use any combination of them to produce a proper weight compensating the unknown one. The set of bodies used in mass or weight measurement is called a series of weights. Since the gravitational acceleration g is cancelled out in both sides of the equation describing the balance of weight, the local variation of the gravitational acceleration does not have any effect on the static mass measurement. Therefore, such measurements can be carried out with a high accuracy by applying sensitive lab instruments called analytical balances. If we know the exact mass of a given body, then its weight is given by the product of its mass and the precise value of the gravitational acceleration at the location of the measurement. By considering the working principle of the static measurement of mass, we will realize that we need to introduce a new concept for mass, called gravitational mass. Let us see how to proceed with it. We have already seen that Newton's second law of motion defines the mass of bodies measuring their inertia, that is their resistance against any effect which attempts to change their state of motion. This type of mass is known as inertial mass. Since the second law states that the inertial mass m of a body times its acceleration a is equal to the force F acting on the body, we can rewrite it as mi times a equal to F, where mi denotes the inertial mass of the body accelerated by the force F. However, we have also seen that in the static measurement of mass the bodies are at rest, when their masses are compared with each other. Since the state of the motion of the bodies does not change during the measurement, that is they remain at rest, the inertial mass of the bodies does not play any role in the static measurement of mass. As a result, the mass of a body determined in the static measurement does not describe its inertia but another property, which we call the gravitational mass of the body. Therefore, in the equation defining the weight g of the body as the product of its mass m and the gravitational acceleration g, the mass is the gravitational mass of the body, and we denote it by mg. Here we do not interpret the gravitational acceleration g as the acceleration of bodies in free fall but as a proportionality constant between the weight and the gravitational mass of the body, which depends on the location of the body. We can also demonstrate the meaning of gravitational mass in the following way. If we measure the weights of two different bodies, for example a ball and a cube, with a spring balance at different locations on the Earth's surface, then we find that the spring stretches by different amounts in different locations, that is the weights g1 and g2 of the bodies depend on the location of the measurement. However, the ratio of their weights, that is the ratio of the weight g1 to the weight g2 is independent of the location. Based on these results, we assume that the weight g of an arbitrary body can be written as a product of two factors, let us say mg and gl, where mg describes an inherent property of the body, and we call it gravitational mass of the body, and gl is a proportionality factor which solely depends on the location on the Earth's surface. Then we see that the ratio of g1 to g2 is equal to the ratio of m1 to m2, which is a constant related to the properties of the two bodies and independent to the location of the measurement. Here the factors mg and gl have nothing to do with the inertial mass and the gravitational acceleration, even their units can be arbitrary. However, we can still establish the equivalence of gravitational and inertial mass. From the second law of motion we see that any force F acting on the body is equal to the inertial mass mi of the body, times its acceleration a. Let us consider the case when only the gravitational force g acts on the body with the inertial mass mi, which is equal to the product of the factors mg and gl. If we choose the units of the factors mg and gl so that their product gives the unit of force, then we can write that the force F accelerating the body is equal to the weight g of the body. As a result, the inertial mass mi of the body times its acceleration a is equal to its gravitational mass mg times the factor gl. That is, the ratio of the gravitational mass mg of a body to its the inertial mass mi is equal to the ratio of its acceleration a to the factor gl. If the body falls freely, then its acceleration a is equal to the gravitational acceleration g, which can be determined experimentally. Therefore, the ratio of mg to mi can be written as the ratio of g to gl. If any object in free fall has the exactly same acceleration g at a given location on the Earth's surface, then the ratio of g to gl is the same for any object at that location. As a result, the ratio of mg to mi is also the same, that is the gravitational mass of a body is proportional to its inertial mass. When we chose the units of the factors mg and gl so that their product should provide the unit of force, we had not specified their units uniquely yet. If we chose the unit of the factor gl such that gl is equal to the gravitational acceleration g, then the gravitational mass mg of a body is equal to its inertial mass mi. Then we can conclude that the gravitational mass and the inertial mass of a body are equal. This statement is the equivalence principle, which is not self-evident but follows from the remarkable fact that the acceleration g is the same for all objects in free fall. However, the universality of free fall cannot be demonstrated in experiments with free-falling bodies or pendulums with the required accuracy. The Equivalence experiment was the first high-accuracy test of the equivalence of gravitational and inertial mass. This photo shows the torsion balance used in the experiment, which could establish the proportionality between the two types of mass with a relative error of 10 to -9. Over the last 100 years several tests have been performed to confirm the equivalence principle, and one of the latest measurements is the microscope project. This was a satellite test, where two sets of bodies of different composition were subjected to the same acceleration. In the experiment it was verified that the equivalence principle is correct within the precision of 10 to -17. Based on these results, we can regard the two types of mass the same quantity, and state that the mass of a body describes both its inertial and its gravitational aspect. That is, if the mass of two bodies are equal, then their inertia and their weight measured at a given location are the same.